Hi guys, welcome back. This video is about the alternating series test. We're going to talk about why it's intuitively true, and I will prove the alternating series test to you using the bounded monotonic sequence theorem. Just as a reminder, this is what an alternating series looks like. So if a series can be written like this, so it's a positive number minus a positive number plus a positive number minus a positive number. So we're adding and subtracting and adding and subtracting, or we start with a negative and then have a positive, and then we have a negative, then we have a positive. And we're adding infinitely many numbers like that together. The terms are alternating between positive and negative, so we call it an alternating series. Now, I'm using slightly different notation than the notation in the Larson textbook. Instead of using a sub n like they do in that book, I'm reserving this a sub n for the nth term of the series, and b sub n, that's just the absolute value of the nth term. So that's the numbers over here whenever we ignore the sign. So remember, b sub n is the absolute value of a sub n. B sub n is always positive. So this is what the alternating series test says. It says, if the limit as n goes to infinity of b sub n, that's the absolute value of the nth term, is 0, and b sub n plus 1 is always less than b sub n, less than or equal to b sub n, for all n greater than some n, then the alternating series that have b sub n as its absolute value of the nth term, those converge. So let's explore this idea a little bit more. Now remember what b sub n represents. It's not the sum of this series. It's not the partial sums. It's just the terms themselves that we're adding and subtracting to each other to get our final answer. So the first part says that as n goes to infinity, b sub n approaches 0. So if I create this sequence b sub n and I graph it, so I graph b sub 1, b sub 2, b sub 3, and so on. As n goes to infinity, those points are going to get very close to y equals 0. That's what the first part says. Now this says that b sub n plus 1 is always less than or equal to b sub n. Now remember what how b sub n plus 1 and b sub n are related. When n equals 1, this says that b sub 2 is less than or equal to b sub 1. So whatever b sub 1 is, let's say it's here, b sub 2 has to be less than that, so it has to be smaller than that. So maybe b sub 2 is there. And b sub 3 is less than or equal to b sub 2, so that's going to be smaller than that. And then we continue in this way, and since b sub n plus 1 is always less than or equal to b sub n, we see that the sequence itself is decreasing. Or excuse me, not decreasing, but non-increasing. Because of that little equals sign, we just say that it's non-increasing. But basically the idea is that it's generally decreasing, except for a few terms when maybe these guys are equal to each other. So they're decreasing, and then they're approaching 0 at the same time. So maybe if I draw this out a little bit further, 5, 6, 7, 8, 9. The terms of our sequence b sub n that we're adding together are slowly approaching 0. So this means that that this term is always smaller than the one before it. That's how b sub n plus 1 and b sub n are related. So b sub n is here, and b sub n plus 1, that's the next one. It's smaller, less than or equal to, and that's true for all n, so we get a pattern like this. Okay, so that's just what the theorem, or the alternating series test says. You might say, why would I even believe that's true? So here's why it's intuitively true. Or why it's true intuitively. Remember how we define convergence of a series. We say that a series converges if its sequence of partial sums converges. So we've got a sequence of partial sums. So it's S sub 1, S sub 2, S sub 3, all the way through S sub n. And remember, we're saying this converges when the sequence of partial sums converges. And remember what the partial sums are. S sub 1 is just A sub 1. S sub 2 is just A sub 1 plus A sub 2. S sub 3, that's the sum of the first three terms. A sub 1 plus A sub 2 plus A sub 3. S sub 4, same thing. Sum of the first four terms. And so on. So this is the definition of convergence of a series. We say that this converges if we can look at the partial sums, and these partial sums are approaching some finite number. Let's call it S. We'll say that this series converges to S when the sequence of partial sums converges to S. And then we write this. The sum as n goes from something to infinity, probably 1 to infinity, something like that, equals S. We call S the sum of the series. Okay, so with that in mind, let's talk about the alternating series test and why it's intuitively true. So I guess we had to do that little aside to remind ourselves what it means for a sequence to converge. Now this time I'm going to graph the partial sums, and I'm going to graph them differently. Rather than graphing them like this, where I'm graphing the set of points, like here I've got n and b sub n. I'm taking the value of the index and using that as my independent variable, and then the dependent variable is the value of the sequence of that particular n. We could do the same thing with the S sub 1 through S sub n here, but I'm going to graph it a little bit differently this time. Instead of graphing this set of ordered pairs, n and b sub n, I'm just going to graph S sub n on a number line. So here's our number line. Let's let let's let 0 be right here. So this is 0 to infinity. And then let's look at the sequence of partial sums of an alternating series. So let's say we're dealing with this alternating series. I have the sum as n goes from negative 1, or as n goes from 1 to infinity, of negative 1 to the n plus 1 times b sub n. So we'll have b sub 1 minus b sub 2 plus b sub 3 minus b sub 4, and so on. That's our series when it's alternating. And we could change this by multiplying everything by negative 1, and then we'd start with a negative b sub 1. But we're just going to look at this particular case. So now let's look at the partial sums. That's what I'm going to graph over here. Now there is no n-axis. I'm just going to graph the numbers S sub 1, S sub 2, S sub 3 on this number line. So S sub 1 is b sub 1, and b sub 1 is positive. So let's say we end up over here. So I started at 0, and I go b sub 1 units to the right because b sub 1 is positive. So b sub 1 and s sub 1 happen to be the same thing. Now let's look at s sub 2. Well, I'm going to take b sub 1, and then I'm going to subtract b sub 2. But remember, b sub 2 is smaller than b sub 1 because of this second requirement of the alternating series test. So since b sub 2 is positive and it's smaller than b sub 1, this is going to be greater than 0. So I'm subtracting a number that's smaller than, or subtracting b sub 2, which is smaller than b sub 1. So I'm basically going to go back this way, b sub 2 units. As I graph on the number line, I'm going from 0 to b sub 1, and then I'm going b sub 1 minus b sub 2 lands me right here. So that's s sub 2. Then s sub 3 comes from taking that, and now we're adding something to it. And this number that we're adding, b sub 3, is smaller than b sub 2 because of this second requirement of the alternating series test. So we're going to add b sub 3, and maybe that lands us over here at s sub 3. And then we subtract b sub 4. And remember, b sub 4 is smaller than b sub 3, so we're right here. And b sub 4 is smaller than that. We're going to subtract that to end up over here at s sub 4. You might say, I don't really get it. What's happening? Well, as I add and subtract numbers that are smaller and smaller, and they're slowly approaching 0, we're going to see this pattern. We go from 0 to s sub 1, then we subtract something, we get s sub 2, then we add something, we get s sub 3, then we subtract something, we get s sub 4. But because these b sub n are smaller, this number that I'm adding or subtracting every time is getting smaller. So these partial sums are getting closer together. So I have s sub 4 plus something small is s sub 5, minus something small is s sub 6, plus something small is s sub 7, then s sub 8, then s sub 9, and s sub 10. I hope you see what's happening. These points are getting closer and closer together to some number. And I'm going to call that S. That's the sum of the series. That's what those partial sums are approaching as n goes to infinity, because we're adding something and subtracting something and adding something and subtracting something and adding something and subtracting something, and those somethings are getting smaller and smaller. So that's one way to illustrate the alternating series test and why it's true. It works because those numbers that we're adding and subtracting from each other are decreasing. So b sub 1 is here, b sub 2 is here, b sub 3 is less than that, b sub 4 is less than that, b sub 5 is less than that, b sub 6 is less than that. And so they're getting smaller, but we keep adding and subtracting and adding and subtracting, and so they're approaching this number that has to be in between eventually. So that's why it's intuitively true. It's not a proof, but you can kind of see what's happening as we add and subtract numbers. We're getting closer to some number in between. Now let's prove that it's true. Now when we prove that it's true, we're also going to use the sequence of partial sums. Because remember, if the sequence of partial sums converges, that means the series converges. And before we actually do the proof, let's talk about the idea of the proof. Here's our approach. I want to show that the sequence of partial sums converges. So we're going to use the bounded monotonic sequence theorem from our first section. To show that the sequence of partial sums converges. Now, it's easier to do this if we look at it in two pieces. We're going to look at this sequence, or we're going to look at the partial sums when the index is even. So we're going to do this in two cases. We're going to show that the sequence of partial sums converges when the index is even. And then we're going to use the fact that the sequence of partial sums converges when the index is even to prove that the sequence of partial sums converges when the index is odd. and we're going to show that those converge to the same value. Okay, so that's the plan. We're going to use the bounded monotonic sequence theorem to show that when the index is even, the sequence of partial sum converges to some number. We're going to call that S, excuse me. Then after we do that, we're going to use the fact that we derived that to show us that when the index is odd, the sequence also converges to S. So if the sequence of partial sums converges to S when n is even, and it converges to S when n is odd, we put those two pieces together, and that means it converges to S in general. So we're saying it converges to S all the time, not just when the index is even or odd. So that's the idea. That's what we're about to do. And first we're going to look at the sequence of partial sums when the index is even. So that's our approach, and we're going to start here. Okay. We'll say we want to show that S sub n converges to S as n goes to infinity, under the special condition that n is even. That's our first goal. So first, let's just look at S sub 2. Well, S sub 2 is the sum of the first two terms of our alternating series. So let's use this one, the version where we start with a positive term. In that case, S sub 2 is b sub 1 minus b sub 2. Okay. Well then, S sub 4, because we're looking at the case of the sequence of partial sums when n is even, when n equals 4, we get b sub 1 minus b sub 2 plus b sub 3 minus b sub 4. It's the sum of the first four terms. But notice that this is just S sub 2. So S sub 4 is S sub 2 plus two more terms. And I think the pattern continues. If I look at S sub 6, that's b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus b sub 5 minus b sub 6. If I group all of these together, those first four, isn't that S sub 4? I hope you said yes. Yes, Miss Townsend, I think I see a pattern. You say, okay, well, what does that have to do with anything? I'll show you. Well, okay. In general, what I've just shown you is that this S sub n is equal to the last term in our sequence of partial sums where n is even, plus b sub plus a couple of extra terms from the original expression over here. So I don't want to keep saying S sub n when n is even, so I'm going to use slightly different notation. I'm going to say this. I'm going to call this S sub 2n, and I'll tell you why. If n is an integer and I double it, now it's even. So when n is 1, I get S sub 2. When n is 2, I get S sub 4. 2 times 2 is 4. When n is 3, I get 2 times 3, which is 6. So noticing our pattern here, S sub 2n is equal to not S sub 2n minus 1, but it's this subscript here is, or excuse me, this subscript here is 2 less than that subscript. So if this is S sub 2n, this is S sub 2n minus 2. And over here, let's look for a pattern in the subscripts. This is an S sub 4, a B sub 5, and a B sub 6 when that's an S sub 6. So these subscripts go up. You know, I've just got a 4, 5, 6 when that's a 6. When this is a 4, I had a 2, 3, 4. So we're going to have a B sub something minus B sub something else. And the index is increasing by 1 as I go across this line. So if this is S sub 2n minus 2, this is B sub 2n minus 1, and then this one is B sub 2n. Okay, are you with me? It's a little bit hard to see. I'm going to draw this a little bit bigger on the next page. Now, if this is confusing for you, if you don't like it, then that's okay. You're actually not required to prove any of this in order to use the alternating series test. It's not necessary to know where it comes from at all. But I wanted to show you where it comes from once. I'm one of those students that really likes to know where things come from. So we said S sub 2 is B sub 1 minus B sub 2. S sub 4 is B sub 1 minus B sub 2 plus B sub 3 minus B sub 4, which we said, hey, look at that, we can rewrite it. That's S sub 2. So another way of saying exactly the same thing is S sub 4 equals S sub 2 plus B sub 3 minus B sub 4. And then we said, well, what happens with S sub 6? Well, you take B sub 1 minus B sub 2 plus B sub 3 minus B sub 4, and then you add B sub 5 minus B sub 6. And we said, hey, well, the sum of the first 4 terms is S sub 4. So this can be rewritten. S sub 6 equals S sub 4 plus B sub 5 minus B sub 6. And we're looking for a pattern here. And remember, S sub 2 is still this. I'm just rewriting that. There was no S sub 0. There's no 0th partial sum. So we notice when we have a 2, a 4, and a 6 here, when this is 4, I get the second partial sum plus B sub 3 minus B sub 4. When this is 6, the subscript is 6, I get the fourth partial sum plus B sub 5 minus B sub 6. Say, okay, well, here's a pattern. If I call this 2n, so when n is 1, I've got 2 times 1, which is 2. When n is 2, I have 2 times 2, which is 4. When n is 3, I have 2 times 3, which is 6. Then this expression over here, look at that subscript, it's always 2 less than the subscript over here. That is 2 less than 2 is 2 less than 4, and 4 is 2 less than 6. So this is S sub 2n minus 2. And then look what happens with the b's. This is 4, 5, 6. That's 2, 3, 4. So this is going to be, the index of this will be 1 more than the index of this. 2n minus 2 plus 1 is 2n minus 1. If I add 1 to this to get that one, we'll get a 2n right there. Okay, so this is a relationship that tells us how these even partial sums are related to each other. So these are the partial sums when n is even. You might say, okay, well, what does that have to do with anything? Well, look at it. Look at where we started. Now, b sub 2 was less than b sub 1, so that made that positive. Because I'm subtracting something that's smaller than b sub 1. You guys with me? Okay, well, actually, it's either smaller or possibly equal, so we should have greater than or equal to sign right there. And then over here I've got this, but b sub 4 is smaller than b sub 3. So b sub 3 minus b sub 4, that's a tiny positive number because this is smaller than this. It's positive. So I've got s sub 2 plus something positive, so this is going to be greater than or equal to s sub 2. And then this is positive or possibly 0. B sub 6 has to be less than or equal to b sub 5, so this has to be greater than or equal to s sub 4. Let's say, oh gosh, what is happening? What's happening here? Well, this shows us something. Let's write down an inequality. 0 is less than or equal to s sub 2. because B1 and B2 might be the same, but most of the time B sub 2 is less than B sub 1, so I subtract and I get a positive number. So S sub 2 is positive or possibly 0 in the case that those are exactly the same. And we just found that S sub 4 was greater than or equal to S sub 2, or S sub 2 is less than S sub 4 if you prefer. And here we've got S sub 4 is less than S sub 6. Do you see the pattern? The next one would be S sub 6 is less than S sub 8, and so on. Eventually we're going to get to S sub 2n is, or S sub 2n minus 2 is less than or equal to S sub 2n. And I'm using the 2n minus 2 and the 2n because these have to be even. Okay, so what does this tell us? If I were to graph these partial sums, S sub 2, S sub 4, S sub 6, S sub 8, that means all of them are increasing. So the sequence, it's really a subsequence of, or a sequence of partial sums. The sequence of even partial sums or maybe we should be more specific, partial sums with even subscripts is increasing. Because I'm taking a number and then I'm adding a little bit something to it, and I'm taking another number and I'm adding a little bit of something to it, and every time I add a little something, that makes it just a little bit larger. Say, okay, it's increasing, but it could be increasing to infinity. So there. Maybe we can't prove this. That's not true. It's not increasing to infinity. We also know one other thing. It's bounded above. And you might say, how do you know that? How can it possibly be bounded above? Well, all of these have to be less than or equal to b sub 1. You might say, I'm not really sure that I agree that that's true. But it is true, because remember when we were looking at the intuitive definition, if we start here at 0 and then we go to s sub 1, which was the same as b sub 1, and then we subtracted something, and then we added something, and we subtracted something, and then we added something, and we subtracted something, and so on. Do you see that all of those partial sums are less than that first partial sum, that first b sub 1? I hope you do. So that means our sequence of even partial sums, it looks like our sequence of partial sums is bounded above, which means, of course, that the even partial sums are bounded above. These guys are always less than or equal to b sub 1. So we've got a sequence of partial sums. It's increasing. I don't actually know what those values are. We don't know what the values are in general. But now I'm graphing the sequence of even or partial sums, or partial sums with even subscripts. I'm just going to use 2, 4, 6, 8, 10, 12, 14, and so on. So s sub 2 has some value. And s sub 4 is a little bit larger than that. And s sub 6 is a little bit larger than that. And so on. But remember, all of these guys are bounded above by y equals b sub 1, that horizontal line. Everything is less than b sub 1. So if our sequence of partial sums is increasing, and it's bounded above, well, according to the bounded monotonic sequence theorem, this sequence of partial sums converges. Now you might say, you didn't prove that it was bounded, you just told me it was bounded above. Well, it is bounded in general. It's bounded above by b sub 1, and it's bounded below by 0. So it's bounded above by b sub 1. It's bounded below by 0. So by the bounded monotonic sequence theorem, the sequence has to converge. And this is the sequence of partial sums with even subscripts. And I made it look like it's converging to b sub 1. That's not true. It's converging to some number that's less than b sub 1 because we're subtracting things from it. So we're going to say that by the bounded monotonic sequence theorem, since this is a bounded sequence and it's increasing, it converges to some number. We're going to call that number S. Okay, so we've got half of them. We have proven that half of the terms of our partial sums are converging to some number S. And I know that this was just part of the intuitive approach. I've graphed the S sub 2n differently than I graphed it over here. Let's look at S sub 2n over here. We started with S sub 1, that was B sub 1. And then S sub 2 was there. S sub 3 was on this side. S sub 4 was on this side. S sub 5 was on this side. So we went to the right, to the left, to the right, to the left, to the right, to the left. And we just kept going back and forth. But if I just focus on the ones with even subscripts, S sub 2 is here, S sub 4 is here, S sub 6 is here, S sub 8 will be next. We're going to have all of the ones on the left side that are bounded above, clearly bounded above by B sub 1, which is way over here. So you can see that the sequence of partial sums is approaching a number if you graph it this way, or you can see it as if you graph it this way, like on a number line. So that's our sum S. These guys are getting closer and closer to S. Okay, so half the time we can prove that the sequence of partial sums is converging to some number S. I'd say, well, what about the other half of the time? Well, let's look at the sequence of partial sums when the subscript is odd. So this is the second part of our proof. I lost my red pen. There it is. Here's another one. Now we want to show that the sequence of partial sums when the subscript is odd, which can be represented this way. When n is an integer, if I double it, that makes it even. If I add 1 to it, take an even number and I add 1, that makes it odd. So now we want to show that the sequence of partial sums when the subscript is odd converges to S as well. So we already know that S sub 2n converges to S. Well, S sub 2n plus 1 is S sub 2n plus the next term in our series. So it's going to be B sub 2n plus 1. And if you're not 100% sure about that, you should expand it for yourself. So let's say I'm looking at S sub 3. Well, that's B sub 1 plus, or B sub 1 minus B sub 2 plus B sub 3. Well, this is just S sub 2. So I'm taking S sub 2 and I'm adding B sub 3 to it. That's just a special case. Or when our subscript is 5, the index is 5, we'll have B sub 1 minus B sub 2 plus B sub 3 minus B sub 4 plus B sub 5. Well, all of this is S sub 4. So you see that? We're taking the previous partial sum and then we're adding one more term. And because of the way our series was structured, that other term is positive. Okay, so we're here. Now let's take the limit of both sides as n goes to infinity. Provided these limits exist, the limit of the sum is the sum of the limits. Oops. Now if you're like, oh my goodness, Miss Townsend, that is a lot of information, that's okay. This is just for you. This is just for you to understand where it comes from. This is not required for testing. I'm not going to ask you to prove this yourself, but I wanted to show you at least once where this alternating series test comes from. So as n goes to infinity, the nth partial sum where the subscript is odd, so we've got the partial sums where the subscripts are odd, is equal to this. Well, we know from what we just did, as n goes to infinity, the even partial sums approach some number, we're calling that s. And then what happens to b sub n plus 1? Well, remember b sub n plus 1, or b sub 2n plus 1. Remember what we said before? The b sub n's, as n goes to infinity, those approach 0. This is saying, just focus on the odd ones. What happens with the odd terms, or the ones with the odd subscripts? And then I'm just focusing on this one, and this one, and this one, and this one, and this one. Well, if the b sub n are going to 0, the b sub 2n plus 1, the odd ones are also going to go to 0. So that's 0. And we've proven that the partial sums converge to s when the subscript is odd as well. So if the sequence of partial sums converges to s when when the subscript is even, and it converges to s when the subscript is odd, in general, it converges to s. And if it converges to s, that means the alternating series that we started with the alternating series converges. And I believe we had negative 1 to the n plus 1, as n goes from 1 to infinity times b sub n. It converges to s. Or you can say that it equals s, same thing. Now you might say, Miss Townsend, we did a whole proof, but we were assuming that it started with positive b sub 1 and then we subtracted b sub 2. How can we prove that the same thing is true if it starts with a negative b sub 1? Well, just multiply both sides of this equation by negative 1. If this converges, if I multiply it by negative 1 times the series will converge. So that'll just converge to negative s instead of positive s. Okay, guys, so that is the alternating series test. Why it's true intuitively, because I'm taking a number and then I'm subtracting something, and then I'm adding something and subtracting something, and then I'm adding something. And because those numbers that I'm adding and subtracting are smaller, when we look at all those partial sums are converging around some point. We're calling that s. So that's why it's intuitively true. But if we want to prove it to ourselves definitively, we can use the bounded monotonic sequence theorem. We looked at the case when the index was even, and we looked at the case when the index was odd, and we showed that they both have to converge to the same thing. And if the even terms converge to s, the odd terms converge to s, then in general the terms converge to s. And that means that the corresponding series converges.